How do you know if an atom is stable? In this video, we're going to learn about radioactive decay. An atom is composed of subatomic particles called protons, neutrons, and electrons. Positively charged protons and neutrons with no charge from the central nucleus. Negatively charged electrons orbit the nucleus. For more information on atomic structure, watch this video. A strong nuclear force holds the positive protons and neutral neutrons together in the nucleus, and is what determines if a nucleus is stable. In stable nuclei, the force is strong enough and brings sufficient energy to hold the nucleus together permanently. Most of the nuclei formed during the Big Bang nearly 14 billion years ago are still in existence today, but not all nuclei are stable. Unstable nuclei either have too many protons or too many neutrons, upsetting the strong nuclear forces. Unstable nuclei try to balance themselves by giving off the excess proton or neutron. This is radioactive decay. Unstable nuclei are radioactive and emit radiation. There are three types of decay: alpha decay, beta decay minus, or beta decay plus. Alpha decay is the loss of an alpha particle. An alpha particle is made of two neutrons and two protons.
Okay, so yesterday some people were kind of questioning me on the parent-daughter thing. So I just want to look at that for a second, okay? Right here, this nucleus has not undergone any decay yet. So that makes him the parent. Once it undergoes decay, so decay, what's decaying? What? Yeah, like if you have a dead animal or a dead plant or something like that, and we say that it's decaying, it's breaking down, it's breaking into pieces, right? So that is exactly what you have in this picture. Here's the nucleus. Does it look the same as this one? No. So once the original, the parent is like the original, breaks into pieces, we get a daughter nucleus, the new one, and then particles. Okay? They're telling us this is an alpha particle. What's it made of right there? Two protons, two neutrons. Who would that be?
This alpha.
Yes, ma'am.
I need to see Grace Flagell in the payroll office for a second, please.
Okay.
Thank you.
Helium. Two protons, two neutrons is helium. So what they say is, in an alpha decay, a helium nucleus breaks off. Okay?
They have a mass of 4 and a charge of +2. When an atom loses an alpha particle, the mass number decreases by 4 and the atomic number decreases by 2. A new element is formed that is 2 places lower in the periodic table. When an isotope has too many neutrons, it decays by beta minus decay. A neutron changes into a proton and an electron. The proton is retained by the atom, while the electron is lost. The lost electron is high energy and is called a beta particle. By losing a neutron whilst gaining a proton, the mass number of the atom remains the same, but the atomic number increases by 1. A new element is formed that is 1 place higher in the periodic table. When an isotope has too many protons, it decays by beta plus decay. A proton is converted into a neutron and a positive beta particle called a positron. Positrons have the same mass as electrons, but the opposite charge. By losing a proton but gaining a neutron means the mass number stays the same. but the loss of a proton means the atomic number decreases by 1. So how do we know if an atom is stable or unstable? We can determine whether a radioisotope is likely to decay and what type of decay is likely to occur by looking at its position on a proton-neutron NZ graph. This graph shows the number of protons on the x-axis and the number of neutrons on the y-axis. This is the stability line. If a radioisotope lies left or right of this line, it is unstable and likely to decay to become stable. A radioisotope that lies to the left of the stability line has too many neutrons and is likely to undergo beta- decay, so give off electrons. A radioisotope that lies to the right of the stability line has too many protons and is likely to undergo beta+ decay, so give off positrons. If particles have a high number of protons, usually more than 82, they are likely to undergo alpha decay. In this video, we have learned that unstable nuclei either have too many protons or too many neutrons, which upsets the strong nuclear force holding the atom together. Unstable nuclei try to balance themselves by giving off the excess proton or neutron either through alpha, beta- or beta+ decay.
If you liked the video, give it a thumbs up and don't.
Okay, so let's actually look at what happens. Okay, first, tell me, what do we call this? What do we call this? It is isotope notation. Can you tell me what we would call that actual isotope? What's his name? Uranium. Just uranium?
Uranium-92.
Not uranium-92.
Uranium-238.
Uranium-238. So I taught you that yesterday. Who doesn't understand? Right here. This right here. He's uranium-238 because that's his mass number. Okay? We did that yesterday. Okay, now, watch what happens when he decays. I'm going to play it a few times, okay? What is it?
Like the little squiggly arrow that went up.
Yeah, what's this say?
Oh, I don't know.
What is the purple big circle? What's the gray? Okay, so look at what comes off of there. Right here. What is that? Say it.
Helium.
Helium. That's a helium nucleus. It's 2 protons and 2 neutrons. And yes, we also have gamma.
I got a question. So, you basically, since you said that like pushed out a helium nuke,
It emits. What does emit mean?
it's like get rid of.
Give off. It gives off a helium. Yeah.
So, with that, does that mean like there would be none of the elements without like that type of decay, or is it just like you? What I mean is without.
You mean you're saying we have to have that decay to get helium?
Well, to get like any of the.
No.
elements. Okay.
No.
Yeah,
No.
That's what I'm saying.
No. Okay. How many protons does he have? 92. Oh my goodness. If y'all cannot take what I've done every day, it's going to get harder and harder. He has 92 protons. How many neutrons does he have? Say it louder. 146. Y'all, 92 protons and 146 neutrons. Is he stable? No. He has way, way, way too many neutrons compared to protons. That's why he's the first one on the table that's the synthetic radioactive at 92. He's radioactive. Remember from yesterday? Okay, so his amount is not a good ratio. He's got too many of one compared to the other. So he's going to be radioactive.
So he has, which one do you have way more neutrons?
He has 146. Is it 46 or 43? 46 neutrons.
Okay, so if it's doing that type of decay where it's like giving off photons and neutrons, then would they still make the uneven because it's taking away
Okay,
photons?
no, we're going to get to that in a second. Hang on. Okay, so first thing I needed you to recognize, he gave off a helium nucleus. Is everybody okay with that concept? He also gave off gamma. That's going to be our radiation that we get. That's the dangerous stuff. Everybody okay with that? Okay, now I want to look at this. Do not pay attention to this piece right here. Cover that up. Okay? Look at that equation. I'm going to give you equations and you're going to have to be able to recognize what kind of equation it is. Look at the back over here, right there. Right here. What do we see? As soon as we see this in equations, it means alpha decay. So right now, all I want you to worry about is this guy right there. We have alpha decay that's occurring. The uranium broke into helium and something else. We'll figure that out in a minute. Is everybody okay with the helium part? Okay, number 2. What do I have now? Carbon 14. I have carbon 14. How many protons does he have? How many neutrons does he have?
8.
14 minus 6 is 8. He has 8. Okay? This is not as an extreme difference. That's why he's not at the bottom with all the other ones that are radioactive. Okay? He's up at the top. But he is still going to be radioactive because in the smaller ones, it's like a 3-to-2 ratio or something like that. Okay? It's still, he's radioactive. So, look at the pieces that you have right here. This is a what? Neutron. Now let's watch what happens when he decays. Carbon 14 decays. Let's watch it again. What's happening? The neutron is changing into a proton. When that happens, it emits, it shoots out an electron. Don't ask me how, I have no idea. When that happens, he shoots out the electron. And yes, we get gamma because there's going to be radiation there. Okay? Now, if we look at that equation, don't look at this piece. I want you to look back here. Right here. What do we see? An E. What does the E stand for? Well, that's what you need to know beta, but what does the E actually stand for? Electron. Look at the number 1. What's with the number 1? A negative. So what kind of decay is this? Beta negative decay. We're talking about 3 different types of decay. Alpha, beta negative, and beta positive. So, if I see an E at the end, it's some kind of beta. I see a negative with it, not negative E. I don't write mine like that. I write negative 1. You see a negative 1, that means beta negative. Okay? Last kind. what element do I have now? Carbon 11. How many protons? 6. How many neutrons? 5. So now I have more protons than neutrons. Let's watch what he does. What's this start out as? What's the purple? Proton. And he changes his proton into a neutron. And what comes out? Okay, a positron. A positron is like an electron. They're the same size, same mass. The only difference is his charge is positive.
So does that mean it would be like inside the nucleus? Because I know regular electrons outside the nucleus, so it's negative.
I know. I said don't ask me how all of it happens and don't let that confuse you. Okay. Just know that in this one, a positron comes out. Everybody cool with that? Okay, so in this equation, don't look at this. Cover that up. Look at what I have on the end. I have an E, so I know it's a beta, and my 1 is, so it is beta positive. Is everybody okay with that? All right, let's write some equations. This is what you're going to have to know how to do for my test. These are called nuclear decay equations. We already did chemical reaction equations. These are the equations that explain the nuclear decaying. Number 1. Okay, so, do y'all think that this thing kind of looks familiar a little bit? Decomposition. What is decomposition? It's breaking down. This is the same thing. We are decaying. Decomposition is the same type of thing, okay? So first of all, what kind of reaction is this? This is a decaying. And in parentheses, we're going to put decomp. Okay? Number 2. What kind of radioactive decay do we see in this equation? What kind is this? Alpha decay. Who doesn't understand why that's alpha decay? You see this right here? This is what you look for. It automatically means alpha decay. Helium. An alpha particle is 2 protons and 2 neutrons. So that is the nucleus of helium. Now, we need to figure out what is AZX equal to. AZX, that's just some letters to hold the place. Okay? But we need to calculate it. So, I've got this guy, and he breaks into this and this. He lost 4 particles from his nucleus. Didn't he? Yeah. So do you have any guess on what our mass is? What's A? What? 205. Here's his mass. He lost this from the mass. That makes sense?
Okay, so anytime you have equation like that, that's what you do.
Yes, so look, I'm going to put the rules right here. All of the things that I put a star by, you got to memorize for the test. Okay? So this rule is the mass goes down 4. Is that the only thing that's going to change?
No.
What else? The atomic number. Yeah. Look, this came out. He had this. This came out. So our atomic number does what? Goes down, decreases. How many? By 2. That's the rule for an alpha decay equation. So in this case, what is Z equal to? 83. Now, X is my element. Can I use, what am I going to use to figure out what element this is?
Periodic table.
I'm going to use my periodic table, and what am I looking at on my periodic table?
For the mass.
I'm looking for the mass.
Mass is like the easiest way to find it.
The mass is the easiest way I could find it. Y'all think we should look for the mass? Is the mass what determines the element? What determines the element? Okay, so the rule is you will never use the mass to do this. And actually, right now, if we look up there, we don't even see a mass of 205. But there could be an equation that you work where you would find that mass. And it doesn't necessarily mean that that is your element. What is the only thing that will identify my element every time? Atomic number. So what element do I have? Huh? Bi. Bi. It's bismuth. How do we feel about that? Everybody's okay with that? It's relatively easy, right? Okay, let's go to number 2. Yes, it is. I'm sorry. It doesn't zoom right away. What kind of reaction we have taking place there? This is breaking into 2. So what do we have? Decaying, decomposition. Now, what type of radioactive decay is this? Beta. Beta minus. Who doesn't understand? Everybody understands that? This tells me right there. Okay? Now we need to figure out what do we get for AZX. What actually takes place in this? We just did it. We just learned it. It's in your notes if you need to look it up. What actually takes place? Mm-mm. Say it louder. A neutron into a proton. A neutron into a proton. Where do neutrons live? Where do protons live? So if a neutron turns into a proton, does the amount in the nucleus change? No. Our mass doesn't change. So A is 60. But our neutron is now a proton. We have another proton. So what's the rule? What goes up? The atomic number goes up 1. So what is Z? Z is 28. What is X? Ni, nickel. This is easy. This is easy. Nope, it's easy. It's easy. Now let me tell you this. This piece kind of seems backwards, okay? When it's the negative one, you're adding. But these at the end, they always tell you what to do. Look. They tell you what to do. You just have to know if you're adding or subtracting. So it's easy. It's not hard. It looks hard.
It does.
It does. You look at it in first and it's like, what the heck? That's like another language. It looks hard, but it's not. Okay, number 3. Yes. Yes, 38 and 19. Sorry, my handwriting is bad. I don't know, actually. I don't remember if I've ever changed that up. I mean, I don't think that, it doesn't necessarily matter, though, because it's saying that this thing is broken into those two things. But I'll have to look. I'll get back with you on that. Okay, so what reaction do we have here? We're still decaying. And they can look a different way, but all of the ones we're going to do are decaying, okay? What are we at, Malachi? Beta positive. And we got to figure out AZX, okay? Well, what actually happens in beta positive? Now a proton is turning into a neutron. So this is proton into neutron. Where do the protons live? Where do the neutrons live? And one's just turning into the other. Am I adding any extra particle in there? No. So does your mass change? Nope. What's going to change? Your atomic number. And my positive is going into no charge. I lost a positive. So what's your atomic number going to do? Go down. 1. Okay, and so once again, this is a positive 1, but we're going to do the opposite math. Okay, so what's A? 38. What is Z? 18. And what is X? Y'all are genius. Are there any questions? No. That's very easy. It does look hard, but it's not.